4 gambling games where your gut is the house's best friend. The casino already knows this math. After tonight, so will you. Number 4. Roulette wheel just landed on red. Again, that's 5 reds in a row. So black is due now, right? It has to balance out. Everyone in the room can feel it. Put your money on black. That feeling, that deep certain sense that black is owed to you, is one of the most expensive mistakes a human brain can make. It has a name, the gambler's fallacy, and entire casinos are built on top of it. So let me show you why the house always wins. Here's the truth your gut refuses to believe. The wheel has no memory. The coin has no memory. A fair coin that just landed heads 5 times in a row has exactly the same chance on the next flip as it always did. 50-50. The past flips are gone. They don't lean on the future. The coin doesn't know it's supposed to land tails to even things out. Each flip is its own separate event, sealed off from every flip before it. So when you feel like black is due, the wheel feels nothing at all. Now, you might have heard of the law of large numbers and think it backs you up. It doesn't, not the way you think. The law says that over many flips, the ratio of heads to tails gets closer and closer to 50%. And that's true. But here's the trap. It does not work by correcting past results. There's no cosmic referee adding extra tails to balance the books. The ratio evens out simply because the early streaks get diluted by thousands of new flips, not reversed. Averages drift toward the middle. They are never pushed there. So if it's all 50-50, how does the casino guarantee a profit? With a tiny, quiet edge baked into every single bet. Take roulette. You bet on red, but the wheel has red numbers, black numbers, and a green 0, sometimes 2. That green is how they win. It means a bet that feels like a coin flip actually pays you slightly less than fair odds. On an American wheel, every dollar you bet is worth, on average, about 5 cents less the moment you place it. Not sometimes, on average, every time. And this is where the law of large numbers turns against you. For a single bet, that 5% edge is invisible. You might win big, you might lose. Randomness rules the short term. But the more you play, the more your results converge on that average, and the average is negative. Play long enough, and a downward drift becomes a near certainty. The casino isn't hoping to get lucky. It's relying on the exact same math you ignored, applied to millions of bets. Time isn't on your side. Time is the house's most loyal employee. Number 3. A coin game with an infinite prize. How much would you pay to play? Let me offer you a game. I flip a coin. If it's heads, you win $2 and we stop. If it's tails, I flip again. Heads now pays $4. Tails again, then heads pays $8. The prize doubles with every tails in a row. So how much would you pay, right now, for one shot at this game? Most people say a few bucks. But the math says you should happily pay $1 million. And almost nobody would. Why would the math say pay anything? Because of the expected value, the average payout if you played forever. There's a 1/2 chance of winning $2, a 1/4 chance of 4, a 1/8 chance of 8. Now multiply each one out. 1/2 times 2 is $1. 1/4 times 4 is $1. Every single term is exactly $1, and there are infinitely many of them. So the expected value is 1 plus 1 plus 1 forever. It's infinite. So here's the paradox. A perfectly rational person, the kind who just maximizes expected value, should be willing to pay any finite price to play because the average winnings are infinite. And yet, you'd have to be out of your mind to pay even $20. That's the St. Petersburg paradox. The math screams infinity. Your gut says absolutely not. So, who's right? There are 2 beautiful answers. First, those giant prizes need absurdly long streaks. To win even $1 million, you'd need about 19 tails in a row, a 1 in 500,000 shot. The infinity is built almost entirely from outcomes that basically never happen. Second, money isn't linear. Your millionth dollar matters far less to you than your first. Bernoulli's fix was to maximize not dollars, but how much they're worth to you. And suddenly the value of the game becomes small and finite. This little coin game is 300 years old, and it basically launched the whole field of decision theory, utility, risk, and how we make choices under uncertainty. It's the reason expected value, all by itself, is a terrible guide when the payouts are rare and enormous. Lottery tickets, long-shot startups, insurance. Your refusal to pay wasn't dumb. It was quietly pricing in risk, and the shrinking value of each extra dollar, the thing's raw expected value forgets. Number 2. The game show question that fooled 1,000 PhDs. 3 doors. Behind one of them, a brand new car. Behind the other 2, goats. You pick a door. Then the host opens a different door, revealing a goat, and asks you one simple question. Do you want to switch? In 1990, a columnist said yes, you should always switch. And over 1,000 people with PhDs wrote in to tell her she was wrong. She wasn't. Let me show you why. Here are the rules, because they matter more than you think. There are 3 doors. 1 hides a car, 2 hide goats. You pick a door, let's say door number 1. Now, the host knows what's behind every door, and the host will always open a door you didn't pick, and always reveal a goat. So he opens door number 3, a goat. 2 doors are left, your door and one other. He asks, stick with door 1 or switch to door 2. And here's where your brain betrays you. 2 doors left, 1 car. 50-50, right? It has to be 50-50. That's exactly what those 1,000 PhDs thought. It feels so obvious that switching can't possibly matter. But that feeling is the trap. Go back to the moment you first picked. Door 1 had a 1 in 3 chance of the car, which means the other 2 doors together held a 2 in 3 chance. That never changed. When the host opened door 3 and showed you a goat, he didn't touch your doors 1 in 3. He just took that entire 2 in 3 and squeezed all of it onto the 1 door he left closed. Your door, still 1/3. The other door, 2/3. Switching doesn't give you a coin flip. It doubles your chances. Still don't believe it? Let's just play. 100 games where you always stay, and 100 games where you always switch. Watch the wins pile up. Staying wins about 1/3 of the time, 33 out of 100. Switching wins about 2/3, 67. Not a fluke, not a trick. The math was right the whole time. 1,000 PhDs just trusted their gut instead. And number 1, the dice trick you can actually use on your friends. Let's play a game. I've got 3 dice on the table, and I'll let you go first. You pick whichever die you want, any of them, your choice. Then I take one of the 2 that are left. We both roll, higher number wins, and we do it many times. Sounds completely fair, right? You even got to pick first. But I will win, not by luck, by design. No matter which die you choose, I can always pick one that beats it. And these aren't trick dice. The secret is something your brain is sure can't be true. Here are the 3 dice. Let's call them red, green, and blue. They're not normal 1 through 6 dice, but they're not loaded either. Each just has 6 numbers. Red carries 2, 4, and 9. Green has 1, 6, and 8. Blue holds 3, 5, and 7. Add up the faces, and all 3 dice have the exact same total. On paper, none of them look stronger than the others. They look perfectly balanced. And in a sense, they are. That's what makes the next part so strange. Let's roll red against green many times and see who wins more often. Compare every face of red against every face of green. Red's 2 only beats green's 1, red's 4 also only beats the 1. But red's 9 beats everything green has. Count it all up, and red comes out on top in 5 of the 9 matchups. So red beats green about 55% of the time. Clear winner. Red is the stronger die. Hold on to that thought. Now do the same for green against blue. Run the comparison, and green wins 5 out of 9. So green beats blue, fine. Red beats green, green beats blue. So obviously red crushes blue, right? That's how stronger than is supposed to work. So let's check. Roll blue against red, and blue wins. 5 out of 9. Blue beats red. Read that chain again. Red beats green. Green beats blue, and blue beats red. There is no top of the ladder. The dice chase each other in a circle forever. This is the trap your brain fell into. You assume that beats works like a ranking, that if A is better than B and B is better than C, then A must be better than C. For heights, for weights, for plain numbers, that's true. But wins more often doesn't have to obey that rule. It's exactly like rock, paper, scissors, where nothing is the best move, just a loop with no king. These dice prove that the simple idea of one thing being better than another can quietly fall apart. And whoever picks second, knowing the loop, wins. The house wins because it trusts the math, not its gut. Now you can too. We drop one paradox every single day. Subscribe and beat your gut tomorrow.